Good evening, everyone. Hi. Welcome. Well, thank you everyone for coming to our final Science Cafe of this series here in Saddlebrook. For those of you who don't know me, my name is Samantha Pierce, but most of you guys know me. I'm one of the program coordinators for the College of Science, and tonight I'm going to facilitate our final journey from Earth's core to the clouds. Now, of course, if you're new to this series, welcome, and if you're returning, we're glad to have you back. And I do want to just remind everyone that for those who are interested, the Desert View Performing Arts Center does stream and upload each of these talks to their YouTube page. I also take those YouTube videos and put them on our Science Cafe website, which is on uascience.arizona.edu. That's also listed in the brochure up front. Now, even though this is our final Science Cafe in Saddlebrook, we would like to encourage you to visit our other venues additional venues that host science cafes throughout the community. Tumamock Hill, Borderlands Brewing, and downtown at Magpie's Pizza, each are venues listed in the brochure. And then if you head over to our Science Cafe website, it's also listed there in addition to the presenters, what they're presenting on, what their research is, and then what the talk is going to be about. Now, even though the University of Arizona's College of Science lecture series is over, the committee did ask that I just remind all of you that if you did miss a lecture, if you did want to revisit any of the material, it is up on their website at uascience.org, and all of them are listed as podcasts. Simply a reminder for the format today. In a moment, I'll introduce our speaker. He will give his presentation. Following the presentation, we will take questions. I'll be going around with the Roman mics. Again, take the mic, ask your question, give it back, so then I can get to the next person. And Dr. Jackson also stated that he would be willing to stay after for a bit to answer some questions one-on-one, and we'll do that for a period of time as well. As you all know, we have amazing research facilities here at the College of Science, especially the Geosciences department. The U of A is always within the top 10 for Geosciences, so if you're interested in more information about the department, we do have their flyers out front. And last little tidbit before we get to the really good stuff, we do have the evaluations out front as well. The feedback really helps us to better facilitate this series and speak to topics that you're interested in, as well as provide feedback to the presenters. On the bottom of that evaluation, there is a place where you can add your email address. I do create the monthly announcements for the upcoming lectures at Saddlebrook, as well as the monthly lectures and announcements for each of the other Science Cafe venues. And if you do not receive emails, do definitely put it there to get information about next series dates and times. The brochure that's out there isn't for the next series. It's still for this one because we do have a few more venues who are going to be giving their talks. So just an FYI about that. But I did get confirmation this morning that for next series, so the one that's going to start in October, the molecular and cellular department. So our department head, Dr. Joyce Schroeder, did give her okay. She does have a few presenters lined up, and they're going to be speaking to molecular cellular biology and health, and then basically that is what goes wrong in the cells that causes disease. Now, without further ado, I would like to introduce tonight's presentation, Using the Past to Reinvent Conservation for the Future, and presenting is Dr. Stephen Jackson. Dr. Steve Jackson is the director of the Department of the Interior Southwest Climate Science Center, a partnership between the U.S. Geological Survey and a multi-university consortium led by the University of Arizona. He received his BA and MS in botany from Southern Illinois University, Carbondale, and his PhD in ecology and evolutionary biology from Indiana University in 1983. Dr. Jackson is an adjunct professor of geosciences and natural resources and environment at the University of Arizona. He started with the U of A in 2012. As the director of the Department of the Interior Southwest Science Center, SGS, his efforts center on fostering partnerships between scientists and natural resource managers to address challenges of climate variability and change. Dr. Jackson continues doing his research in ecological history and paleoecology, focusing particularly on the past 25,000 years as a series of natural experiments in which we can observe directly the ecological consequences of environmental changes of various rates and magnitudes. Some fun facts about Dr. Jackson. In his spare moments, he trains horses, edits translations of Alexander von Humboldt's writing on nature in the early systems, and enjoys living and hiking in the Tucson Mountains. Tonight, Dr. Jackson will discuss on how the conservation we practice was largely developed in the mid to late 20th century and was founded on the ideas of environmental and ecological stability that prevailed in the science of the time. In the past few decades, we've learned a lot from the geological record about environmental and ecological changes that have taken place in the past 100,000 years. The perspectives of history forces reexamination of some of the most widely accepted and closely held assumptions of conservation. Reinvention of conservation, based on knowledge of past environmental change, will make conservation more effective in a rapid changing future. Will you all please help me in welcoming Dr. Stephen Jackson?
Thanks. Oh, and I think this is, oh, it is on. Okay, good. Thought there was a switch to be flipped. Yeah, thank you for the invitation. It's great to come up here and enjoy some of the cool air in Saddlebrook, and I realize it's an honor to be standing on a stage that has been previously occupied by Roy Clark and the Oak Ridge Boys and the Smothers Brothers and all kinds of great people. That seems a little loud. Is that okay? Okay, good. So by day, I am a bureaucrat. As Samantha mentioned, I am director of a partnership between USGS and the University of Arizona. I'm actually employed by US Geological Survey, but I'm deeply, deeply embedded at the University of Arizona. And I actually work for the Department of Interior, so I'm a scientist working as a bureaucrat, working for the resource managers, the water managers, forest managers, fish and wildlife managers through the whole alphabet soup of interior agencies, as well as the Forest Service, state agencies in the Southwest, county and municipal governments, a broad spectrum. I won't be talking about that specifically, but if you're interested in what we do at the center, just Google Southwest Climate Science Center and we'll pop right up and you can read all about us. I neglected to bring brochures, but it can give you an idea of what we do. So I am going to start with a little bit of a self-confession that I have spent virtually my entire life playing in the mud. Starting when I was at least as far back as I can remember, when I came home covered with mud at 5 years old, and my older brother gleefully hosed me down, much to my chagrin. But I actually found out how to get paid to do that. So for the past 42 years, which is 2/3 of my life, I've been getting paid to play in the mud. As a paleoecologist and scientist. And these pictures just show some representative shots of the kinds of things that we do. We go out on lakes and ponds and collect core samples of the mud that's accumulated at the bottoms of the lakes, and use the chronological sequences, the vertical profiles, as sort of strip charts of environmental and ecological change over hundreds to thousands to tens of thousands of years. We also do this sort of thing in peat bogs and peatlands and wetlands and estuaries and excavations, as in the lower left. Really any place that preserves old mud, I'm all for. And starting about, 20 years ago, I started working on what's not really mud, but is also old stuff. Again, if it's old, I'm all for it. The picture on the lower right shows a very large pack rat midden in central Wyoming. So here we think of pack rats as these annoying little creatures who climb up into our cars and eat the wiring and the brake linings and things like that, and cause large amounts of financial damage. But in the right kinds of places where people don't live, they're actually very useful as botanists in a sense, or collectors, because pack rats collect stuff and they pack it into their dens. Many of you have seen the little dens that they make around in the yard. They particularly like rock overhangs and crevices, and they build their dens in there and build them out of the local flora. So what they're doing is just sampling the local plants, packing it in those dens, pooping and peeing on the dens. I'll talk a little bit more about that in a moment. And actually, the rat urine actually helps preserve the middens so that if they're in a dry place, a protected overhang that's sheltered from seepage, sheltered from rain or snow or sleet, they can be preserved for hundreds to thousands to tens of thousands of years. So we just go crawling up in the rock and with rock hammers smashing out pieces of the middens, taking them back. We date them with radiocarbon dating and then try to find out what's in there. So I'll talk a little bit now about, just start with some stories from the past. So this is Wind River Canyon in central Wyoming, just north of the Bighorn Basin in that photo. And you can see the green there is woodland that's dominated by Utah juniper. It's the juniper that you see all over the Colorado Plateau and throughout the Great Basin. And it reaches its northern limits up on the Wyoming-Montana border. And there's also another species, Rocky Mountain juniper, which is another one that you'll see up in Verde Valley and up on the Mogollon Rim that co-occurs with it. So we hit the rocks and collected a bunch of these things. And this is actually only a small part of the total midden, which was probably originally 5-6 times this size. This was a piece that I retained just as a show and tell thing. And you can't see it from there, but I'll leave these up here if y'all want to look at them. It's got this hard rock-like rind. I mean, we take these out with hammers and chisels. And that rind is actually crystallized rat urine, which protects it from weathering. It protects it from water, and it's got antimicrobial properties. I haven't figured out how to market it as a medicinal yet, but I think it has potential. But inside the midden, this surface is juniper fronds, and if you look at it closely, these look like dead juniper fronds that fell off the tree yesterday. This is 3,700 years old, 3,700 years old, and it looks like it just came off the tree. And what's in it are Rocky Mountain juniper. All the juniper in there is Rocky Mountain juniper. There's no Utah juniper in there, all Rocky Mountain juniper. And there's also something called black sagebrush, which doesn't grow in the canyon. It grows nearby and on upper slopes, but not in the canyon. So just in the past 3,700 years, we're seeing some ecological change. Utah juniper moved up from the Wyoming-Utah border and has taken over this woodland as the dominant, which was originally Rocky Mountain juniper. Now Rocky Mountain juniper is just in the wettest places, the shady places, the seepage areas, and Utah juniper has really come to dominate that slope. So let's move south of the border to Coahuila, Mexico, in the Chihuahuan Desert near Cuatro Cienegas. This is a canyon that has typical Chihuahuan desert scrub, the same kind of thing that you would see if you drove just 100 miles west of here at low elevation. Yuccas and barrel cactuses and choyas and ocotillos and creosote bush and so forth. And I was doing some field work up there and just thought it was completely unrelated to pack rat middens, but I thought, well, gosh, there's rock. Let's look in some of the crevices. The first crevice I looked in, I found this midden. Again, very hard, rocky outer texture. Cracked it open, and none of these species are in that midden except a little bit of yucca. What's in it instead is pinion needles and hull fragments, juniper fronds from a local species of juniper, and oak leaves, the scrub oak leaves, the really tiny ones that you might see up in the chaparral parts of Arizona. That midden is 17,400 years old. So this is considerable change. It's much more, it's a longer period of time, but it's also a lot more change than we saw in Wind River Canyon. And then the last story is going back to the U.S., to Dutch John Mountain, which is right on the Utah-Wyoming border, just north of the Flaming Gorge Dam. And today, this is pinyon juniper woodland, the same kind of thing that you would see if you went up around Show Low or just east of Flagstaff or many parts in the Mogollon Rim. It's pinyon pine, Utah juniper with Rocky Mountain juniper. And again, we collected, gosh, I think by the time we were done, about 100 middens from that site. This one I kept just because it's really interesting, because it's full of Douglas fir and limber pine and spruce, blue spruce. So that one turns out to be 27,000 years old. So what would it take? So, you know, for either the Mexican or the Utah example, let's ask ourselves, what would it take to turn this pinyon juniper woodland that's there today back into forest of limber pine and Douglas fir and spruce? Lower temperatures and more water. Yeah, that's exactly it. And you can get more water by lowering the temperatures, or you can add more water, or both. In this case, it's probably a little bit of both. So 17,400 years ago, the Laurentide ice sheet was still on top of Chicago and Detroit and virtually all of Canada, Vancouver and elsewhere. 27,000 years ago, there was ice over most of Canada. So these are going back to the Ice Age, when things were cooler and circulation patterns were such that the things were actually wetter through much of the Southwest and some of the desert regions of the Rocky Mountains. So I use this to illustrate 2 points. One is that we can use these old things, even though you know, it is petrified pack rat poop and a lot of interesting botanical material, but they're rich, they're treasure troves of information. We can use this to learn about the past. And secondly, that this indicates that things do not stay the same. We live on a very dynamic planet where the environment changes and ecological change happens. And so for the next few minutes, I'm going to be talking about ecological change and giving you, again, some examples, and then we'll explore some of the implications of those examples for conservation, particularly in the face of a changing climate. So, as I mentioned, for the past 42 years, I've been kind of obsessed with time and what happens in time. I'm going to start with a brief digression to set this up. So we're going to go out of Paleo and we're going to look at the Colorado River right now, which is a really important river hydrologically and ecologically and economically for the region. It's got its headwaters up in on the west slope of the Front Ranges, in the interior ranges of Colorado, the Wind River Mountains of Wyoming, the Uintas of Utah, and then it flows down through the deserts through the Grand Canyon, and eventually makes it somewhere past Yuma, and then it disappears because all the water gets diverted to various places and no longer gets quite to the Gulf of California. But a really important question that's out there that water managers, whether they're with Central Arizona Project or Bureau of Reclamation, Corps of Engineers, or any of the municipal or regional water utilities and commissions, they're really interested in knowing how climate change, as projected in the climate models, will affect Colorado River flow. And it seems like a pretty easy question because we're talking about a fairly simple physical system. We're talking about the atmosphere and watersheds and runoff and infiltration and river flow. So it's all physics, ultimately. Should be a fairly straightforward problem. And so it's an interesting question scientifically and an important question societally. So that's a great combination to send scientists riding to the rescue to answer this question, armed with their computers and their Bayesian statistical models and data crunching capacities and so forth. And there has been a series of studies over the past 20 years published in some of the most prestigious journals, scientific journals and geophysical journals in the world, journals that undergo rigorous peer review. And the studies that are out there trying to project Colorado River flow from general circulation models give highly divergent results. Almost all of them project a net decrease by the late 21st century. But the magnitude of the decrease varies widely from 6% to 45% reduction. So if you're a water manager, that's a huge difference. I mean, it matters that flow is going to go down, but 6% planning water management for a 6% reduction in flow is a whole different world than planning for a 45% reduction in flow, which is really drastic. And so understandably, this has created a lot of confusion in there. And again, these are scientists, these are first-rate climatologists and hydrologists who are doing this work, and they're coming up with different answers. And that's confusing to all of us who are trying to follow this, and certainly confusing to the water managers. There's a very nice paper, actually, I guess it's its 4th anniversary now, by Julie Vano and a very large group of climatologists and hydrologists and water managers who they brought in to look at why we're getting so many different answers. And basically it's because going from an atmospheric profile, from a general circulation model, just a characterization of the atmosphere, to a stream flow estimate, even though it's all just physics, there's no single right answer. There's no single correct method to get from here to there. There are a number of different methods that are out there that each require different kinds of parameterizations, different kinds of data, different kinds of statistical treatments, and we really don't know. We don't have any way of discriminating among which ones are more right than others. And they're all right to some extent because they're providing us with information about the system's sensitivity, but in terms of actually making a prediction or a forecast, we have no basis to discriminate them. We could wait until the end of the century and figure out which one's right, but it might be right for the wrong reasons. The truly correct model may not give the number that actually works out, or the model that gets the physics best may not be the model that plays out, because again, there is a lot of complexity here, and that complexity is again modeled in different ways, but again, there's no single right answer here. This is a physical system, a simple physical system, and I use this as an example because I'm an ecologist. And when you add ecology, you're adding living organisms, and you're adding all kinds of complexity and dimensions that are beyond the physics. So this makes understanding or forecasting how ecological change is going to play out in the future very, very challenging. And one of the things that I like about the paleo record is it gives us all of these natural experiments that at least give us an understanding of, okay, we had a climate change of a particular kind 2,000 years ago. What happened here ecologically, and what happened over here ecologically? And we can start to at least figure out what are the right questions and what are the right mechanisms and processes that we want to look at. So the main reason I bring this that example up is that it's a really good example of something that's being called post-normal science. And post-normal science originally developed by these sociologists. And actually one was a political scientist, the other was a sociologist, but they define post-normal science as when the decision stakes are very high. And of course, the decision stakes can't get much higher than when you're talking about the Colorado River flow that provides Central Arizona project, Las Vegas, Los Angeles, San Diego, Imperial Valley agriculture, Yuma area agriculture. Those are pretty high stakes. So we've got high stakes, and we also have high fundamental uncertainty that is going to take a long time to resolve scientifically, if we can resolve it. Again, these are really, really hard problems. We're making progress. We're learning as we go along, but there's certainly still a lot of uncertainty in any kinds of forecasts that we can make. So I'm going to segue from here to argue that that conservation itself, conservation of natural resources, is similarly in a post-normal phase, or should be coming into a post-normal phase, because ecosystems are already changing. We're seeing them undergoing change because of various kinds of stresses, particularly the droughts and the heat waves that have hit the entire western U.S. Over the past 2 decades are having huge effects on forests and woodlands and shrublands and grasslands. This was taken just a year ago in Sequoia National Park. All of that brown and orange are trees that died the previous summer in what's really an epic drought that they're probably going back into in California. So we're seeing ecosystems under change. We saw things like this happening in the Rocky Mountains a decade ago. With these are all being driven by bark beetle outbreaks. This is the mortality in lodgepole pine forest in Wyoming. But the bark beetles are on the move because summers are getting warmer and they're getting longer, and that's allowing the bark beetles to build up bigger populations. Instead of 1 generation per growing season, they now have 2 generations, so they can double or increase exponentially through time. So we're in a period of ecological change, and I think one of the most robust forecasts I can make as an ecologist is that we're going to see things happening on the landscape that we've never seen happen before. We're going to see emerging novelty. And I say that with confidence, partly because we're already starting to see it, Catalinas, and partly because of what I see in the paleoecological record. Now, there's been a lot of talk of anthropogenic novelty, and certainly the things that we're doing with land use and harvesting and biogeochemistry and so forth are causing obvious changes. We are altering the planet. We've been altering it pretty intensively since the Industrial Revolution, but people have been having at least local to regional effects going back thousands of years. Of course, Jay Quaid was here a couple of months ago talking about this. So we're, as I think he argued, we're in the Anthropocene, or fabulous Anthropocene, as this artist put it. But there's also natural novelty that happens, and this is the emergent change that I've been talking about. So this is a profile, a vertical profile, and also a chronological profile from a tiny, tiny little pond in the Ozarks near the Missouri-Arkansas border. This is today. This is 20,000 years ago at the height of the last glacial maximum. Today, the Ozark uplands are oak and pine forests. Back then, they were pine and spruce forests, but instead of shortleaf pine, this was jack pine, the kind of pine that you would find up in the Canadian Shield now, again, reflecting the colder conditions back then. But what's interesting is this period between about 16,000 and 10,000 years ago, the transition from the boreal vegetation to the more oak-dominated vegetation. And we have a really peculiar mix of open forest with a lot of ragweed. So that indicates that the canopies are opening because you can't grow ragweed without a lot of sunshine. Open forests that are dominated by oak and spruce. Oak and spruce. Where can you go and see oak spruce forests in North America today? Really nowhere. There's, their ranges overlap, but only just a little bit. So oak and spruce, but also with hickory. And with elm and ash and hawthorn beam and maple, species that during this period are actually more abundant than they have been at any time since or at any time before that we know of. This is characteristic not only of the Ozarks, but we see this in Wisconsin, Minnesota, Ohio, Pennsylvania, Kentucky, Tennessee, on down to northern Georgia. The entire Ohio River and upper Mississippi valleys were occupied by this kind of vegetation, which has no modern counterpart. You cannot go anywhere in the Midwest. You cannot go anywhere in Eastern North America. You cannot go anywhere in the world and find vegetation that looks like what we're seeing here. So from the perspective of today, this is a novel community. This is something that we have no direct experience with. And this indicates this is part of that turnover. This was an unusual climate that has no counterparts today. It was hyper-seasonal with warmer summers and cooler winters overall than today. I can explain the physics of that afterwards if anybody's interested. But basically, it was a peculiar climate that's driving the formation of peculiar vegetation. We're taking the species we have on the landscape today, and we're just arranging them in different combinations under these different kinds of environments. So this is the past. I think this is what we have to look forward to in the future. And everywhere we go, we see the same kind of turnover. From the perspective of someone living back in the Pleistocene, the Sonoran Desert vegetation would look really weird. During the height of the glaciations, this area was pinyon juniper woodland, and you would not have found a saguaro or any of this typical vegetation pretty much anywhere. But today, of course, this is what we have. The mesquites came in. Oops, sorry, there. Yeah, the mesquites came in about 12,000 years ago as the pinyons and junipers died back. The saguaros came in about 9,000 years ago. The Palo Verdes have only been here for about 4,000 years. So if we were just 5,000 years ago, the desert would look a little off. It would be like, where are those green barked shrubs? So even here we see that kind of thing. This is a nice example from a study we did in the Michigan Upper Peninsula. It's the last 8,600 years of history, again, going from the present back to 8,600 years ago. And I won't go through all the details, but the main things I want to note is now this is classic UP vegetation, hemlock, beech, sugar maple, yellow birch forest. But if you look at one of the dominants, beech, it's only been there for 1,500 years. It's only been part of that landscape for the last 1,500 years when it crossed the Mackinac Straits and spread into the UP. So even 1,500 years ago, you'd start to see things that are a little bit different. And then all of these, and this is a neat record because it has pollen and macrofossils of all of the forest dominants of the UP now. And you can see them just kind of coming and going. Here's spruce, it peters out as things warm up into the, after the ice retreat. Here's jack pine when it's cool and dry and it disappears and goes off to the sand plains. White pine up and down and up and then kind of crawling around. Paper birch. And then just sort of pinching out 4,000 years ago and not coming back, but yellow birch coming in and taking over the landscape. Hemlock going way up and then having 2,000 years of rarity on the landscape and then coming back. So we've got continual ecological turnover. There's no period more than 1,500 years long at this site where we don't see some major change in the dominant trees in the forest. One of the dominants going down or some new kid moving in or someone who's local but rare expanding their populations. And this is tracking different kinds of climate changes and disturbance regimes and so forth. So a high turnover situation here with relatively little stability. We can go other places like South Carolina, where we've just worked up this record from the coastal plain, and here things have been relatively quiet for the past 4,000 to 5,000 years, really the past 6,000 years. landscapes compared to what we saw in Upper Michigan. Between 20,000 and 30,000 years ago, nothing happened. It's really boring. So even though there was environmental change there, but the vegetation wasn't really responding. But then we have this period between about 16 and 6,000 years ago when we've got a lot of turnover. There's a lot of action, a lot of dynamics. But even in systems that seem fairly stable, eventually you get to a point where the environment changes enough and they transform. They tip over and turn into something else. This is one of my favorite examples because ecologists tend to think of the tropics as a very stable place. But this is an 86,000 year record by a group from Florida Institute of Technology from the Guatemalan uplands, tropical rainforest. And oops, looking up the wrong thing. Tropical rainforest that shows, again, I won't go through all the taxa, but you can see that this is a very busy record. There's a lot happening here in 86,000 years. And there are periods of 4,000 or 5,000 years where not much happens, but eventually something happens and the vegetation undergoes some kind of transformation. And this is really typical all over the world. Everywhere we go, every continent, whether you're at the equator or towards the poles, whether you're at sea level or up in the mountains, every vegetated continent has records that show this kind of dynamism. Novelty isn't new. So let's explore this, thinking about the future and drawing some lessons for future climate change and variability, just keeping in mind this very wise proverb that I think is valuable just as a reference point. So this paper was one we published, I guess it's now on its 11th anniversary almost, but what we did was explored the consequences of that particular generation at that time of climate simulations and look at the different combinations of 4 variables: July temperature, January temperature, July precipitation, and January precipitation, just 4 simple climatic variables. And what we were interested in was looking at the combination of those 4 variables and how they played out in space. And one of the interesting things was that under the A2 scenario, this has been superseded in the latest IPCC assessment, but it's representative. In the A2 scenario, which is the most extreme scenario for greenhouse emissions and climate change, there are climates, particularly in the tropics, but also at high latitudes and even mid latitudes, that disappeared. Particular combinations of those 4 variables that go away, that you don't find anywhere, just like particular combinations of those seasonal variables 16,000 years ago don't exist today. Those climates disappeared. Here, climates that we are familiar with are projected to disappear. And novel climates, again, particularly at the tropics, but also in many other parts of the world, novel climates, realizations of those 4 variables in concert that don't exist anywhere today are projected to emerge. That means that by the end of the century, according to these forecasts, we will be seeing climates that have no counterpart in our current experience. We can't go anywhere in the world to look at them and look at what they mean ecologically, what kind of vegetation, what kinds of communities might develop under those circumstances. We have no experiential basis. We have no instrumental or measurement basis. We have no historical basis. So to me, this puts a lot of uncertainty into ecological forecasting. Even if we nail the climate perfectly for the end of the century, there's still an awful lot we don't know about the ecological responses. Except that there will be responses. We may be seeing some manifestations of this already in some of the kinds of things that are happening. The California drought of just a couple of years ago is a good example. This is one where 2014, which was really the height of that drought, was unusually dry by the standards of the past 1,000 years or so, or 700 years, sorry, I got my math wrong, the past 700 years from tree ring records. This was an unusually severe drought in terms of the effect of dryness, but the precipitation anomaly is nothing big. I mean, there was a precipitation deficit, but bigger precipitation deficits in the past have led to milder droughts. So in this case, the drought severity was being driven by the record high temperatures that California has been experiencing winter and summer, particularly in the winter though, for the past several years. And if you dry the atmosphere out, you increase in a nonlinear fashion the atmospheric demand for water. The hotter the atmosphere is, the more water it demands from the plants, from the soil, from the reservoirs, from the rivers, from the snowpack, and so forth. And that's what, so it's an accelerator or amplifier of drought, and that's what we're seeing. And so this is a drought of a type that has not been experienced ecologically in California, even over the past several centuries. A complication I'd like to just talk about very quickly too is that climate change is a redundant expression. It's, you know, it's almost a trivial observation, but climate changes. It varies and it changes. It's part of the world that we live in, you know, we can see. I mean, we all remember wet and dry and hot and cool years. This is the red is the instrumental record in the Upper Colorado Basin for the 20th century. The black is tree ring reconstructions of that moisture variation or precipitation variation. You can see the tree rings track it pretty accurately. University of Arizona has the Laboratory of Tree Ring Research, which has been for the past century and remains the premier tree ring facility and laboratory in the world. It's the Vatican for tree rings. This trace down here was developed by Dave Miko and Connie Woodhouse from the Tree Ring Laboratory. These are reconstructions for the past 1,200 years of annual precipitation in the Upper Colorado Basin. And this is the instrumental record. It's been smooth, about a 30-year smoothing. But the point I want to make here is first that it's highly variable, and also that it's not just random variation around a constant mean. It's a continually evolving system. The averages are changing through this time period, and the variance is changing. You see periods where the variance is very reduced. You see periods where the amplitude of the variation is very high. You can see that, you know, these ramp downs and sudden abrupt changes. No 2 years in a decade are alike in this record. No 2 decades in a century are alike, and no 2 centuries in the past millennium are alike. This is a continually evolving, highly variable system reflecting atmosphere-ocean interactions, complex interactions involving the atmosphere, ocean heat transport, particularly in the tropical Pacific, and also the land surface, and also the cryosphere, the ice packs and ice sheets that are all interacting in this dynamic way to produce this highly variable system. And so what we're going to be seeing over the next few decades, the next few centuries, is an interaction between these natural components of the system and their natural variability with the different kinds of forcings that are being imposed by human activities, greenhouse gases, land use, which has a number of feedbacks, and so forth. And so again, even if we can predict with accuracy and precision the average state of the climate in, say, 2100, there can be 2 or 3 dozen different pathways to get from here to there, depending on these interactions, which we are not in position to forecast very well. This is very difficult stuff to forecast. We're still trying to understand the dynamics, and it's not easy. But looking at the ecological implications, ecological systems have memory, and they're full of contingent outcomes. Disturbances and recruitment events interact with climate variability to produce different kinds of outcomes. And so actually, this is a good example. This was the Mustang Fire in 2002, which was in that pinyon pine, that pinyon juniper woodland that we talked about earlier on the Wyoming-Utah border. This was a very hot fire that took out all of the old growth pinyon and juniper. And I haven't been back there in several years, but 7, 8 years after that fire, there was no regeneration of the pinyons and junipers. It was mostly cheatgrass, a few native grasses, a few prickly pears, but the trees were not coming back. And that's because this fire happened during a severe drought, so there wasn't water enough to really be able to support the seedling populations. So that system has transformed, possibly irreversibly, into something else. So there are these historically contingent ecological outcomes. The Catalinas burned in 2006. Get that right? When there was the fire up at 2003. Okay, thank you. So yeah, the Catalinas had a very severe fire in 2003 that took out an awful lot of the old growth ponderosa, also took out part of Summerhaven. Summerhaven is regenerating, only with nicer, bigger houses. But the ponderosas, for the most part, aren't coming back. If you hike in the areas that burned, it's now robinia, thorn scrub, and oak, gamble oak woodland, really thickets of that. You see very, very little ponderosa pine regeneration. And that's because, again, like the Mustang fire, that fire happened during a drought period. And the only way you can bring those ponderosas back is to have a really wet winter and a wet spring and a strong monsoon. That's what it takes to regenerate ponderosa pines, and we have not had that circumstance. And so they're not going to come back. If we have another fire that takes out the rest of the ponderosa pine this summer, unless we have a really wet winter next year and a reasonably wet spring and a strong monsoon, those ponderosas won't come back. So there are these different kinds of contingencies and legacies. And one of the consequences of that is that under a similar climate of the future, you can have several different kinds of ecological realizations. And this is one of the things that I've seen throughout my career in looking at these kinds of dynamics. Where you've got the same environment, but different things happening in those environments depending on their history. All of these legacy effects, all of these contingent effects. Oops. Oh. So just a quick forecast. There will certainly be losses with climate change. And again, looking back at the past, there have been losses. The Irish elk. I mean, a lot of the megafauna, it's still open to question how much of that was human hunting. Paul Martin from UIA arguing for overkill by human hunters. But for Irish elk, it's really clear that that was climate. They went out in places long before humans arrived during a period of climate change. Here's a species of spruce, Picea critchfieldii. It was the dominant tree in the lower Mississippi Valley during the last glacial period. It extended all over the coastal plain in the southern Appalachians, and it's gone. It disappeared about 13,000 years ago. People didn't kill that off. That's probably a climate-driven natural extinction. So there are costs to even natural climate change. Here are some extant species: cheetahs, red pine of the Great Lakes and St. Lawrence region, Torrey pine of the Southern California coast, moose that have very, very, very low genetic diversity. Actually, Torrey pine has no genetic diversity within it, no significant genetic diversity. These are species that have gone through severe bottlenecks in recent time. They have skated right to the edge of doom. pinched out into very low populations, near extinction, and they were lucky enough to pass through the filter and re-expand. So we've got vestiges of past climate change and vestiges of near extinction experiences or near-death experiences, and we do have an increasing number of documentations of actual extinctions. So there are costs to this. So, you know, we can despair about this, and believe me, it is disconcerting. We've got a strange new world coming. It's hard to predict contingent outcomes. Things are happening really fast, and it's you know, it's really tough to predict. But one of the things that I take away from the fossil record is that there's also hope that we get from history, because all of this diversity of life that we see on the planet has been through a lot. It's been through fast climate change. It's been through large magnitude climate change. It's been through different kinds of variability. And there have been costs. There have been extinctions. There have been genetic losses. But what we have on the planet has persevered. And for me, that gives me a little bit of hope, because it indicates that most species have capacity for adapting to climate change. And the idea that's fortunately now, I've been preaching this for about a decade now, but people are really starting to understand that this is an opportunity to learn and to figure out how we can leverage these natural capacities for climate adaptation in natural populations to use to advantage, because we're not going to be able to save every species. We'll never have the resources or the capital to be able to do intensive interventions. So we can be much more efficient with our resources by figuring out what's already out there that we can leverage and manage, and then put our resources into the things that really, really need it. So this is a segue to my last section. Life adapts to changing environments. Shouldn't conservation adapt too? I'm going to say something provocative here. If the goal of conservation is to prevent change, then it's going to be a failed effort. We're doomed. Even without human activities, even without rapid climate change, ultimately conservation will fail if the goal is to prevent change, because we live on a planet of change. Climate's going to change. It varies, and it will change whether we like it or not, and whether we're accelerating with it with our own activities or not. So we need to really incorporate this into conservation thinking, which is slowly happening. I think we also need to recognize that conservation it's not a science. It is an intersection of science and values. Conservation is a place where the science and the values, ethical, aesthetic, economic, utilitarian, all come together and interact, which is a really important point. We know that scientific knowledge and understanding change through time. Science has been around for about 500 years, since the scientific revolution. I have here Francis Bacon's Silva Silvarum, or Natural History. And this was published in 1650. This is their original volume. And so, you know, we know that we've come a long way. Bacon helped get us started and helped get the scientific enterprise going. But if I just go to a random page and start reading, there's some pretty weird stuff. It's somewhat strange that the blood of all birds and beasts and fishes should be of a red color, and only the blood of the cuttlefish should be black as ink. A man would think that the cause should be the high concoction of that blood, for we see in ordinary puddings that the boiling turneth the blood to be black, and the cuttle is accounted a delicate meat and is much in request. Which, yeah, I ordered some the other day. But, you know, there's good stuff in here, but a lot of it is pretty weird, because science has evolved a lot since the scientific revolution. We're not doing it the same way Bacon was doing it, and an awful lot of the stuff that we're doing today would look really weird to him. An awful lot of the stuff we're doing today in science that's legitimate science would look really weird to a scientist from 1908 or 1918 or 1958. Societal values change. So looking at this mountainscape, if you were living in the 1600s, let's say during the scientific revolution, if you looked at this kind of scene, what would come to mind would be wilderness, wasteland, devastation, just intimidation. This would be a terrifying landscape, a landscape of terror where there were no people, no green fields, and so forth. In the Romantic era of the 19th century, and from Humboldt to John Muir, the reaction would be grandeur, awe, awe-inspiring, inspiration. For someone, a hiker in the 1970s, it would be, wow, this is a great place to go backpacking and show off my legs. Now we might think, for someone in the 19th century, it might be minerals. We can go dig some holes and get some metals out and get rich. Today, we look at it and we often think of ecosystem services, water supply, hydrological regulation in the rivers, snowpack, and so forth. And these aren't mutually exclusive. We still, I can hike and enjoy them. I can appreciate the economic values and the utilitarian values, and I can also get a deep sense of awe and inspiration from this. But the point is that society's perceptions change. And so if our science changes and our values change, then conservation, the intersection of those values should change as well. Another prop I brought is the John Evelyn Silva, which was the first, as far as we can tell, the first English language conservation text published in 1670. It was about forest conservation in His Majesty's realm, His Majesty's timbers, which England wanted for obvious reasons. And we know that conservation has changed an awful lot. The conservation of today is very different from what it was then. Today's conservation largely derives from mid-20th century science, post-World War II science, and from mid-20th century and late 20th century values. Starting with inheriting from the Progressive Era and Theodore Roosevelt and Franklin Roosevelt's New Deal and the different conservation programs that got developed then, the science that was done then. But it really accelerated in the 50s, 60s, and 70s up through Earth Day with the science of the time, and the science and society relationships of the time, and the values of the time, as reflected by Rachel Carson and Aldo Leopold and other great conservationists and naturalists. But we're still, in conservation, largely living in that, we're sort of living in the 1970s in a lot of ways. And if you look at the conservation literature, you see a lot of controversies. These are in the scientific journals. These are all titles from the scientific journals, and these are prominent academic ecologists and biologists who are wrangling over different kinds of things about whether ecological novelty is something we should accept, whether we can do assisted colonization, whether new conservation is good or bad, whether we should try to eradicate every alien invasive species or learn to live with some of them, et cetera, et cetera. And although these are superficially dressed up as scientific controversies, they're about values. These reflect values issues, even among the scientists, and not all of us are honest enough or introspective enough to really own up to the fact that that what we're doing in conservation is value laden. I tend to be on the more progressive end of those arguments, and the argument that I try to make to the people who really want to keep things in 70s style conservation is that progress is not a zero-sum game. I think there's a fear that we will lose all of the progress that we made in the 50s and 60s and 70s and 80s by yielding on any of these issues. And I disagree. Progress is subsumptive. We still use 17th century physics. Even though we know that Boyle and Newton were wrong, Einstein and Heisenberg showed that, you know, they didn't get it right. It's not as universal as they had thought. But we all drove cars here. Those are all based on classical physics. You know, there's no, we're still using that stuff because it's useful. It doesn't go away. We're living in this country on a constitution that was written in the late 18th century based on 18th century philosophy and political theory, and a whole lot of philosophy and political theory that derives from the ancient Greeks and Romans, who the founding fathers read very carefully. And we're still using it. It's not obsolete. It's under stress. It's been amended. It's changed in various ways over the past 250 years or so, but it's still there, and we accept that and we use it. We're still working under 20th century conservation policy, the Wilderness Act, the Endangered Species Act, NEPA, the Clean Water Act, and so forth. And we don't have to give those up. We don't have to just say, okay, we're going to surrender everything that happened in the 60s and 70s that we think might be good for the environment and go back to square one. We can build on this. These are laws that were developed based on the science of the time and the values of the time. The science has changed. The values are changing. Climate change was not on the radar back then. No one was thinking about that. They were thinking about a very static, constant kind of environment. And we're getting in some areas where the laws are not quite in accord with where the world is going. But we don't have to give up the past progress to be able to move forward. I think we can adapt conservation to the changed science and values without abandoning that progress. So just a few last points. I guess the last one is that there's a transformation that's underway in climate science and ecological science that the Southwest Climate Science Center is part of. What we're trying to do is bridge the gap between the communities of research and the communities of decision. And we're doing this by trying to develop more effective, more direct engagement between the science and the people who use the science, whether it's the public or, in the case of the center that I run, the various decision makers in the various government and tribal agencies and private sector and NGO sectors who need good scientific knowledge to be able to make decisions that we can't afford to use the 1950s or 1970s or 1990s modes of we're scientists, we're just going to tell you what to do, or we're scientists, we're going to publish our papers and someone will come up and use them. We're actively engaging to try to get the managers to understand the science, and also for us to understand what their concerns are so that we can provide them with the knowledge that they're going to need to be able to make good decisions. So thanks.
Questions?
Steve, have you been able to make this presentation to the Nature Conservancy, and if so, have they taken any of your ideas?
Yeah, I've made the presentation to people, to audiences that included TNC people, but not to a Nature Conservancy audience per se. There are a lot of people in the Nature Conservancy who are with a lot of this, who really get this. Of course, TNC is a very large, diverse, complex organization, so I can't speak for every wing of it, but there are, I think, a lot of the conservation NGOs, even more. Universities are very conservative, and I think actually where the most progress needs to happen is in the academic sector. I think in the management sector, the resource managers I work with, they get this, and I mean, they may not understand, they don't understand it in a deep sense, but intuitively, this makes sense to them in terms of what they're actually seeing and trying to do. And I get the same sense across a lot of the NGO sector, including TNC. And I think where you're seeing the big bruising battles are in the universities, which is interesting, but it's a whole nother lecture. But universities are the most conservative institutions in this country. They change very, very slowly. And change is happening there. But again, in institutions like universities, it tends to be generational. People have to die and retire and get replaced before things really change. Because, yeah. That was one of the reasons I left the university after 30 years as an academic. I just decided that wasn't the place where the action was. That's why I went over to the sector that I'm in now.
Was Al Gore right or wrong?
Depends. Actually, I'll make a confession. I've not seen either of his movies, so, and I haven't read his book, so that's a tough question to answer.
Could you give an example of maybe what the newer approach to conservatism would be in relation to a traditional approach to conservation?
Yeah, I think I would distill it down to accepting change and as inevitable, and then learning to going beyond that to figuring out how to use change as our friend and to manage systems as they change. So change is a threat. It's by no means do I trivialize the threats of environmental change and climate change to ecosystems, to biodiversity, but it's also there are elements of change. We simply have to accept that because that's the world that we're in, and whether or not humans are driving climate change, whether or not climate change is accelerating by human activities or accelerating for mysterious reasons that nobody knows, but we do know that it is accelerating, then we have to accept that and work with that. So I guess my most general, actually my other perspective is that this perspective from the past, that change is natural, that nothing ecologically is permanent. Communities that we tend to think of as these things that have been around since time immemorial are all relatively recent. The sequoia groves are only a couple of generations old, and before they were there was something else there, and the sequoias were somewhere else. So I think that gives us permission in an ethical sense and a pragmatic and in other senses, but particularly in an ethical sense, it gives us permission to do more or to risk more in conservation and restoration with change. That we have, and part of these controversies I alluded to are whether or not we should use the natural state as the reference point to restore back to or to try to maintain. But it turns out the natural state is evolving, and for many places, because of these contingencies and legacies from the past, we can't discriminate between natural states. There may be more than one justifiable natural state. In other words, the state of a particular unblemished system today or undisturbed system may be an artifact of a particular series of events that happened 500 years ago or 200 years ago or 1,000 years ago. And that if that event had not happened, that natural system and that natural state today would look very different. And so to me, that gives us it gives us permission to embrace more than just whatever happens to be arbitrarily on the landscape, and gets us to focus more about what we value about those things on the landscape. Because I think naturalness, it's a very slippery, squishy concept. And self-confession, I went into ecology and into historical ecology because it was a search for the natural. I wanted to see what the continent looked like back before people came in and cut down trees. And you know, one day about 15 years into my career, it dawned on me that, isn't it interesting that everything I see is flux? You know, there is no, you know, that natural state just was not there. So I think that does give us, I think it gives us, it allows us to focus on the particular values. Again, the conservation is inseparable from values. The particular values, whether you know they're ethical, they're aesthetic, they're religious, they're utilitarian, they're economic. There are lots of different values that we get out of conservation, and it allows us to say, okay, well, what is it that we want to get? I think for aesthetic and ethical and economic and other reasons, we should try to keep those sequoia groves in good shape as long as we can, and try to ensure that for future generations, they will be able to enjoy something like that. There are other situations where I'm willing to let go of some natural state of a system because it's simply unsustainable. We don't have the you know, it's like trying to hold back the tides. We're simply not going to be able to do that, and so we have to accept the change and figure out how to work with it. That was a little long-winded, but it was a tough question.
I'm sure you're aware there's a lot of people who are interested in getting rid of invasive species. Would you say that that's kind of misguided?
No, absolutely not. It's I would say that efforts to eradicate every invasive species everywhere is misguided because it's impossible, and we can't do it. So what we have to do is figure out, some invasive species are really not doing much harm, and there are a few that are actually doing things that are valuable to us in various ways. There are things like cheatgrass, bufflegrass, etc., that are doing serious damage and constitute major threats to things that we value. And in those cases, by all means, we should manage them intensively. That said, there are people who advocate for absolute eradication of bufflegrass. And if I had a magic bullet to make bufflegrass disappear in the Southwest, I'd fire my gun. But that magic, we're not going to find that magic bullet. In the meantime, we need to be using our resources in strategic ways to control and eradicate and manage bufflegrass in the places where it constitutes the greatest threats and where we can mobilize the resources to do it. And of course, that's the really heavy lift out of that.
One of the touchstones that hit me pretty hard when I was a student was Population by Paul Ehrlich of the population bomb. And we don't seem to, it doesn't seem to have much impact in today's recognition. And so much of what seems to be going on appears to be how many people are using how much resource. I'm a bit of a student of geologic change over time, and it's pretty dramatic if you look at long time periods, and what can't be more dramatic than that. But in terms of speed of change, just look at what California looks like today compared to what it looked like when I was growing up there in 1960 and 50. And to me, that challenge of understanding values that can no longer be held back because locusts, we are the locusts, so to speak, and not just us. And our population is relatively, the rest of the globe is moving rapidly. And all of that is contributing to it. So one of the things that I guess I'd like you to comment on is the weight we put on in terms of solving people problems, as opposed to, and part of that is understanding variation and change.
Yeah.
It's the people problems that I think we.
Yeah. No, the people problem is, I mean, yeah, that's really at the heart of this. Of course, is what we do, ultimately, so the business that I'm in is climate adaptation, which is basically saying, okay, climate varies, and climate is varying, and climate is changing, and it's going to change, and how do we deal with that to help the resource managers address what's going on? There's a whole nother area that I don't work in, which is mitigation, but that's ultimately, the human activities are driving most of the threats that are out there to these different kinds of things that we value. Again, climate change, land use, harvesting, invasive species, translocations, biogeochemical alterations, and so forth. What is, I guess, what probably keeps me up at night? I'm more optimistic than many, maybe most of my climate change ecology colleagues about nature in the short run. Just because I think there is a lot of natural adaptive capacity. Because again, it has to be there. They wouldn't have been able to survive. But that's all. At the same time, there are going to be losses. That capacity is not infinite. But what keeps me up at night is that we're putting that stress is being exerted on nature, broadly speaking, at the same time that there are all of these other stressors that, we have land use change, we have fragmentation of the landscape that makes it more difficult for many species to be able to move and adjust their ranges. We have invasive species that are adding new pressures. And so it's those interactions that I worry about. And then, of course, in the longer run, just natural adaptation it's going to buy us years to decades. But eventually, if climate change continues on the trajectory that it is, and at the rates that it is, eventually it's going to outstrip the natural capacity, and it'll ultimately outstrip our capacity to do it. So, in a sense, we're trying to keep things in as good a shape as possible and build enough and maximize the natural resiliency that's out there and be able to prepare. But again, there will be limits to a lot of these systems. Inevitably, though, I think we're already in for change, and we're seeing it. The West is a really prime example. That's I tell my friends in the East, if you want to see the issues that you're going to be dealing with in Georgia or New York or Pennsylvania or Michigan, come out here. If you want to see what you're going to be dealing with in a couple of decades, come out here and see what's happening in the Rockies, in the Sierras, in the Colorado Plateau, and in the Sky Islands, because this is kind of a, sorry, I'm not sure why it does that. This is kind of a glimpse of the future. If, again, we continue on the paths that we are.
On the simplest level, some of us use conservation easements, feeling like something good is going to become of it. And, sitting and listening to all this, it just sounds like a very short-term Band-Aid on thing.
Yeah, conservation easements are valuable, and they because they help with that connectivity. They give nature a little bit more space for things to happen, and so a conservation easement may not prevent the disappearance of a particular type of ecosystem or the disappearance of a particular species population 25 or 50 or 100 years down the road, but it does buy it some time and may help it get in position to be able to adapt. And also, if you've got a conservation easement for, let's say that we design one for desert tortoises or for cougars, and it turns out that in 25 or 50 years, the cougars or the desert tortoises or whatever can't live at that elevation or in that particular habitat anymore, the easements can still be useful for other stuff, for other species. And so, and I think in the same way as, Joshua Tree National Monument. The climate projections suggest that at the end of the 21st century, Joshua trees are not going to be growing in most of that monument. Now, I actually don't. I have a few quibbles with the science, but let's just postulate that they're right. So we have a national monument. The Joshua trees are gone, but there are other species like the Washingtonias, the palms, or some of the other species of that region from lower elevations or further south that may be able to use that habitat. We may need to rename it Mojave Foothills National Monument or something like that, or the Joshua Tree Memorial National Monument. But so there is still utility in that. But this is something that, going back to the Nature Conservancy comment, that I think the conservation organizations, led primarily by the NGOs and by some academics, are really starting to think about of how do we, historically the Nature Conservancy would buy or swap for a piece of land and then develop the easements or manage it themselves or turn it over to an agency and assume that that was, okay, we have preserved the habitat for this species in perpetuity. They're realizing now that in perpetuity doesn't really mean in perpetuity. And so they're starting to struggle with this very complex question of how are we going to most efficiently allocate our resources in this changing environment so that the purpose of a particular land parcel that an NGO invests in, or a land trust or whatever invests in, if its particular utility or conservation value decays in 25 years, then what do they do? Do they hang on to it and let it depreciate? Do they sell it and use the proceeds to purchase habitat somewhere else that's critically needed at that time? That's a really tough problem. And it's got even more compounded uncertainties than what I've been talking about, because you're adding economics and human behavior and lots of intangibles. But that conversation is now going. I think it's just starting to develop some momentum.
So I know we're about at time, so please help me in thanking Dr. Jackson for coming out today. And he did say that
feel free to come up and examine these beautiful, interesting pack rat mittens or these smelly old books.